Hello, today we are going to do number 23.26 in the book Matters and Interactions, Volume 2. And the question is, a bar magnet is dropped through a vertical copper tube and is observed to fall very slowly, despite the fact that no mechanical friction between the magnet and the tube is quite high. So it's negligible. We have to explain this carefully. So here's our magnet falling in our tube, and it says that because the bar magnet is falling, the bar magnet creates an electric field that goes out of the north into the south, but because it's falling, it's getting farther away. The magnetic field at this first loop is getting smaller and smaller, and the change in magnetic field causes an electric field, a curly electric field, to occur on the loop. Now the loop doesn't like this change in magnetic field, and we'll see. We'll try to counteract that change. So let's go look at that. We have this formula which just shows that there will be an electric field with a change in magnetic flux, which is happen if you have a change in magnetic field and will cause, therefore, a current. So we have this loop in the magnet, and it's falling. And you know that we said earlier it goes north to south. So here we have our magnetic field at this loop going down, initially going down. A bigger one, but then eventually we get after some time of falling, it gets very small, like half of what it was before. So we have to find the change in magnetic field. And so what we have to do is we have to ask ourselves, what do we have to add to the initial to get to the final? Well, the answer is you have to get one that points up, because this is getting smaller. But we want the negative dB dt to find our curly electric field, because, as we said before, this loop does not like the change. It doesn't like any change, so it wants to counteract this change. So negative dB dt is going down. So we're going to draw the curly E in the direction of I in the loop. And how we do that is we use our thumb and we point it in the direction of negative dB dt. So it's going to be curling around. It's going to go like that. So in relation to this picture, it would be this way. Is what you eventually get. So that's how we got that. And now, if you look at that, we have to analyze what the B field that we have at this loop. Because the current is going this way, we're going to have a magnetic field going down. It's going to be going down. So our magnetic field is going down. So basically that means basically the same thing as the magnetic field. It looks awfully similar to one that's created by a magnet that looks kind of like this, because it's going out of the north into the south. It's the same thing. It's going down into the south. And as you can see, these guys are, the North Pole and the South Pole are going to attract each other. So this just reassures the fact that we know that this loop does not like the change. It's going to, they're going to attract each other, as in this magnet, this part, the loop is going to basically stop or want to stop this falling. It won't stop it, but it'll slow it down because of the attraction. And so it slows down, and that's why there in the problem it says we had to explain why this happens, why it falls very slowly, and that is why it falls very slowly, because the loop does not like change, and it will do things to counteract that change in magnetic field it gets from the falling bar magnet. Thanks for joining. Bye.